Alright, so this is FRQs, and so in this FRQ we are on Practice 1, Section 2, Part B. There's no cuts that are allowed, and we are going to rewrite both function g of x and h of x in a simplified expression. And so we do not want any part to have a negative exponent. We also need to state if we have a domain that needs to be adjusted, we need to state that. So let's get started. I know that this can become an exponent and an exponent. So this right now is going to be condensed into the ln of x cubed minus the ln of x to the 1/2. Okay, by the way, keep in mind really quick that x to the 1/2 is equal to the square root of x. And when that occurs, we know that the smallest number that we can plug in is 0. So I already know that x's have to be greater than or equal to 0 for the domain. Next, I'm going to take this and condense this into one ln function. As we condense it, we're going to take subtraction and change it into division. X cubed over x to the 1/2. When you have the same base and you're dividing, you can take the exponents and combine them by subtracting the top minus the bottom. I'm going to use the McFarlane or the butterfly method. 3 times 2 is 6. Subtract 1 times 1 is 1. All divided by 1 times 2, which is 2. 5 halves. So g of x equals the ln of x to the 5 halves. But what I do need to add to this is I need to add to this that x values have to be greater than or equal to 0. Why is that? Again, we can't have a negative. We can't have a negative value going into a square root function and producing some type of a real answer. Let's go ahead and let's look at the second part. Okay, and we're going to do the same thing. We are going to put this into a simplified form, and then we always need to make sure that we account for things like, for instance, square root in the first part of A, knowing the value, the domain is going to be adjusted. Down here, before I even get started, I see that we know that we can never have 0 in the bottom, so I'm asking myself, what value could I plug in for x and I'd be in trouble, because we now have a function that produces an outcome of 0. We don't ever want to have 0 on the bottom, so keep that in mind. We never want to have this thing equal 0. If it does, 0 is in the bottom, and we've broken a math rule. It would be undefined. So I'm going to rewrite. I know sine squared is the same if I think of sine squared plus cosine squared equals 1. It's one of our memorized trig identities. So I'm going to replace sine squared with 1 subtract cosine squared. 1 subtract cosine squared x minus 1 all over the cosine of x. So 1 subtract cosine squared x minus 1 all over the cosine of x. The 1s are additive inverses. They combine to 0, cancel out, and then now I have negative cosine. Well, cosine squared is cosine times cosine all over the cosine of x. And so they're going to simplify, and I'm left with h of x is equal to negative cosine of x. But what we have to keep in mind, just like we adjusted the domain for part A, is that this can never equal 0. So the cosine of x can never equal 0. Okay, let's look at part B of number 4. Solve g of x for 0. So I'm going to look up to this function. Now remember, g of x is like a y. So we're asked, when does y equal 0? Whenever y equals 0, we're looking for the x-intercepts. So find the x-intercepts on this function that go from 0 to pi over 2, including those endpoints. Okay, so if I want to know when is g of x equal to 0, notice g of x equals this quantity. I can replace j of x with 0. Now, in both the front and back, I have a cosine of x. So let's factor that out. And I'd be left with 2 sine of x minus 1. I want to make sure I did that right. Cosine of x times this quantity, good. Cosine of x times this quantity, great. Now, this goes back to a really simple concept we've learned a long time ago. If the statement is true, then what can we assume? We assume that either a is 0, so 0 times any value of b equals 0, or we could assume b is 0 because any value times 0 equals 0, or maybe they're both 0. So let's apply that same concept. Either this quantity equals 0, or this quantity equals 0, or they both equal 0. So where is the cosine of x equal to 0? Well, here's the function. the cosine of x is equal to 0, or the x value, think about it, is equal to 0 at pi over 2 and also at 3 pi over 2. But it states that we only want to find the values that are between 0 and pi over 2, including those endpoints. So that would be from here up to here, including the endpoints. That means that we can eliminate 3 pi over 2 and only have one answer of pi over 2. Let's do the next part. 2 sine of x minus 1 equals 0. I'm going to add 1 to the opposite side, and then I'm going to divide by 2, and I'm going to ask myself, where is the sign equal to 1/2? 1, 2, 3, 1. So 1/2 is the y value, or the sign, at 1 pi over 6 and also at 5 pi over 3, but we're asked to only list where is g of x equal to 0 from 0 to pi over 2, including those endpoints. That means only at 1 pi or pi over 6. Let's look at the second part of. Alright, so we are now in the second part of B, and it says solve for k of x equals 3x. So just like I did with part A, in part A I was able to take j of x equals 0 and replace j of x with 0. Now I'm going to replace k of x with 3e. So I have 3e equals 8e to the 3x minus e. Okay, so my next step here is what can I combine? So if we're going to combine e's, they have to have the same exponent. So notice how these e's have the same exponent. So I'm going to add e to the opposite side. So 4e equals 8e to the 3x. And then let's go ahead and let's divide here. So let's divide. It doesn't matter which one you would do. It really doesn't matter which one you do. But let's go ahead and let's divide here by 8. Now if I divide by 8, I have e to the 3x equals 1/2 e. And our goal is to solve for x. The only reason we learn about logs is so that we're able to solve for a variable that's in the exponent position. So I'm going to take log base e, that's what I'm trying to remove. What I want to remind you is log base e is the same as ln, or natural log. And as long as you do it to both sides, you'd be okay. So log base c and e, or if I wrote ln here, they're going to simplify, and I have 3x here. And I'm going to rewrite this here, and I can change this back to an ln. In fact, does it say that it wants us to write it as an ln? I should go back and see here. But whether you write log base e or ln, we know they're equivalent. So ln, and this is 1 times e. 1 times e is e. 2 times 1 is 2. So this is where I'm at right now. Okay, then I'm going to go ahead and I'm going to recognize that I can take this and expand this. I know that division turns into subtraction. So I have ln of e minus ln of 2, okay, equals 3x. And now I'm going to divide by 3 to the right and divide by 3 to the left. So x equals ln of e minus ln of 2 divided by 3. Now remember, log n is the same, natural log is the same as log base e. And so why am I writing this is when we have the base and it's the exact same as the number behind it, it simplifies to a 1. So here I have 1 minus ln of 2 all divided by 3. Okay, let's look at this one. So we are on part C right now, part C. And part C, if I go to, it says, with the function m, we provided m of x equals the cosine of 2x plus 4. Find all the input values, so all input values in the domain of m that yield the following output. Now when it says all input values, remember that doesn't say 1 revolution or 2. It says as you continue to go around, where will we always find an outcome of 9/2? So this is the outcome. My input is this. This is my output. Input, output. So I'm going to write 9/2 equals the cosine of 2x plus 4. Alright, so then my next step here is I'm going to go ahead and I'm going to subtract 4 to both sides. So I have 9/2 minus 4, or 4 over 1 equals the cosine of 2x. I'm going to do that McFarland method or butterfly method here. We have 9 times 1 is 9. Subtract 2 times 4 is 8. All divided by 2, and I get 1/2. Alright, where can I find a cosine of 1/2? Alright, positive cosine of 1/2. 1, 2, 3, 1, 2, 3. So it's going to be right here is a positive cosine. So one answer would be at pi over 6. Again, it's a positive 1/2, and down here in quadrant 4, we can find cosines that are positive, so it would have to have a reference angle of 60 degrees. The other one would be at 5 pi over 3, or 10 pi over 6 reduced. Now, keep in mind, this isn't just an x, it's a 2x. So what does that mean? Well, now I need to isolate the x, so I'm going to divide by 2 here, divide by 2, divide by 2. When you divide by 2, it's like multiplying by the reciprocal. So this is pi over 6 times 1/2. So 1 pi over 12, and again here is going to be 5 pi over 6. But here's the key. When it says find all input values, that's not saying that you're only going to go one time around or twice. You can go as many times as you want. We just want to know when is the output going to be 9/2. So we need to find a way to represent how you continue to go revolutions around how do we end up with 9/2. So to do that, I feel confident in an answers here of 5 pi over 6. I feel confident, and so what I'm going to do, notice something before I wrote my final answer. I said this, and instead of saying 2 pi over 6 or pi over 3, I wrote pi over 6. Pi over 6 is right here. This is pi over 3. So let me go back here and change this to a pi over 3. I found a mistake there, pi over 3. So I end up with pi over 6. Pi over 6. This position where we can find a cosine of positive 1/2 is pi over 3, not pi over 6. So I feel confident of these, but how do we say that it can go around an infinite number of revolutions and still get an output of 9/2? So to represent that, we say it can go around as many times as you want, so that's plus pi over n, where n is any integer. Now let's make sure that is correct. Let's just check. So let's grab a calculator really quick. And I'm going to go second plus 712. I'm going to go to where my mode is in radians. Perfect. I'm going to come up here. I'm going to plug in the cosine. Actually, I'm going to put a 4 in front. So 4 plus the cosine of 2x looks great here. And now I'm going to graph it. And I just want to test that, first of all, this works. So if I put in a value of, let's do 1 pi divided by 6, I should get an outcome of 9/2, or 4.5. Awesome. Let's do another one. Let's come here and do 5 pi over 6. 5 pi divided by 6 also gives me 9/2. But how does this adding on to this, an n pi plus pi n, how does that make a difference to represent an infinite amount of solutions with an outcome of 9/2? Let's go up here and show you again. So let's make sure, let's just choose a random number here. Let's try like 4. So if I have 1 pi divided by 6, and I'm going to add to it 4 pi. I'm just completely coming up with that. Now, I do need to adjust the windows. So let's make sure we go all the way out here. Let's go out a long ways just to make sure that I can adjust for that. Put a really large number, and let's come up here again and do this. So again, 1 pi divided by 6, and I'm going to add to that a random integer like 4. So 4 pi. Now if I get an answer of 4.5 or 9/2, which I do, it proves to me that this works, and we could do the same down here. Let's come down here, and let's do 5 pi divided by 6, and I'm going to add to it, let's try 4 again, or try 6 or 5, right? It could be any one of those, and it better give me 4.5 or 9/2.